You think you're safe right now. You sit with a deep, unquestioned sense of security that the chair beneath you will support you. The walls will stay in place, and the floor won't disappear for a moment. This security is an assumption you've been taught since childhood. But this assumption isn't reality itself. It's a curtain your brain has constructed to keep you afloat. Because the human mind didn't evolve to perceive the world as it is. Rather, it had to simplify, form fixed assumptions, and suppress danger to survive. If you constantly knew that everything around you is actually 99.9% empty space, that atoms never truly touch, that everything you perceive as solid is just microscopically vibrating probabilities, you wouldn't be able to go to work, make decisions, and would most likely collapse mentally. That's why your brain tells you a story. In this story, objects are stationary. Time flows only in one direction, causes precede effects, and the world continues to exist the same way even if you don't look. This story is comforting. But here's the problem. Modern physics, especially quantum mechanics, shows that this story is not true. And this is not a metaphor. This is not a poetic narrative. This is the cold result of experiments repeated, measured, and verified for over a century. Stop for a moment and imagine this: that a decision you make tomorrow could affect an event that happened yesterday. That two people could look at the same physical system and get completely opposite, but simultaneously correct results. That you cannot determine the state of a particle until you look at it. This is not science fiction. This is a direct consequence of quantum mechanics. Over the past century, the world's brightest minds, from Einstein to Bohr, from Wheeler to Bell, while trying to understand the foundations of reality, realized that what we thought was solid ground was actually a thin layer of ice. And this ice cracked a little more with each new experiment. We often see science as a tool that explains the world more clearly. But in the quantum world, science blurs things instead of clarifying them. Measuring changes the system instead of explaining it. Looking is not neutral observation, but active intervention. The experimental setups used in laboratories today are not blackboard equations. They are engineering marvels powered by lasers, mirrors, silicon chips, and atomic clocks. And these machines force reality to confess. They say the same thing every time. The universe doesn't have to conform to your common sense. At this point, it's perfectly normal to ask the question, why is this important for my life? Because quantum mechanics doesn't just explain the strange behavior of atoms. It questions our fundamental assumptions about causality, time, objectivity, and even the role of the observer. In other words, it raises the question of what reality is. That's why Einstein was disturbed. Not because he didn't understand quantum theory. On the contrary, because he understood it very well. If these equations are correct, and experiments have shown this time and again, the universe is not a clockwork, predetermined machine. Rather, it is a strange and unintuitive system shaped by observation and composed of probabilities. Einstein searched for a flaw until the end of his life. God doesn't play dice, he said. But the universe answered, dice are being played. And the numbers that come out are values that classical logic doesn't allow. Today we have moved beyond the question of, is this really happening? The real question is, what does this mean? And this is where the darkness begins. Because if reality is not independent of observation, If time is not as straight a line as we think, if cause and effect can be reversed on a microscopic scale, then perhaps the solid world we live in is a thin veil stretched over a much deeper, much more chaotic structure. What we will do now is this. We will not tear this veil, but we will carefully lift it from three places. We have three quantum paradoxes before us. Each targets a different pillar of your common sense: time, reality, and the observer. And the most disturbing part is this. None of these paradoxes have yet been solved. There are no answers. Only experiments exist. And there is a truth that these experiments whisper to us, but which we dare not say aloud. The universe is far stranger than we think. Perhaps we are not as central as we think, or perhaps we are at the very center. In the next section, we will begin with the first paradox, with an experiment that questions whether time truly remains in the past. If you are ready, let's continue. Now, let's pause for a moment and ask the question again, but this time in a more unsettling way. Could a decision you make right now affect the behavioral history of a particle that existed long before that decision and then ceased to exist? This is different from time machines in science fiction, because here no one goes back in time, nothing is rewound, and no alternative universe escape is used to resolve any paradoxes. Instead, quantum mechanics does something far more insidious. It implies that the past is not as fixed as we think. At this point, the topic shifts to something even more unsettling than time travel. Because time travel, at least intuitively, has an understandable story. Someone leaves, something changes, and the consequences emerge. But here, the cause and effect chain ceases to be a chain. The effect precedes the cause. The choice is made after the event. But the universe acts as if it were waiting for this choice. That's why we move on to the second important issue: space. Because if time is unreliable, distance cannot be expected to be very reliable either. In everyday life, information transmission is extremely simple. If you want to tell someone something, your voice travels through the air. If you send a message, the signal passes through towers. If you wave, the light reaches their eyes. All these processes have one rule in common: information travels, and this travel has an upper limit. Nothing travels faster than the speed of light. This is one of the most immutable principles of modern physics. But quantum mechanics stops at this point and says, we don't send information, but we are still connected. The phenomenon we call quantum entanglement shows that two particles, whether a few meters or a few light years apart, can behave as a single system. These particles don't send signals to each other. They don't communicate. They don't coordinate. But the moment one is measured, the other simultaneously enters a specific state. The distance between them is completely meaningless for this behavior. This doesn't technically eliminate the concept of distance, but it renders it dysfunctional from the perspective of our physical intuition. Because what matters here is not where they are, but that they are part of the same mathematical definition. Space is merely the background scenery in this relationship. And if your mind has endured this far, we now come to the most difficult question. This is a topic even physicists speak of in whispers: the winner's friend. This thought experiment brings the famous Schrödinger's cat from the laboratory to the human world. The question is simple but devastating. What happens when two conscious observers look at the same event and see two mutually exclusive results? And worse, what if mathematics says both are true? At this point, the problem is no longer particles. The problem is reality itself. If there is no single objective truth that is the same for everyone, what is science measuring? According to whom are experimental results true? Is there a world independent of the observer? Or is what we call the world completed by observation? This question frightens physicists. Because if this door is fully opened, science will have to question not only nature, but also its own fundamental assumptions. And this is precisely where we begin to return to the basics. Time. You don't need an academic education to understand how time works. You know it with your body. You go from childhood to old age. Wounds heal but leave scars. Fire burns, then goes out. Nothing flows backward on its own. We call this the arrow of time. And this arrow is the backbone of all our experiences. Psychologically, the past is a closed file. The future is an open field full of possibilities. This distinction makes regret, hope, responsibility, and free will possible. But when you look at the equations of physics, this arrow disappears. Newton's laws of motion, Einstein's equations, even the Schrödinger equation are symmetrical in terms of time. That is, mathematically, the rules that apply when you play a process forward also apply when you play it backward. The equations make no moral or physical distinction between future and past. So why do we remember the past but not the future? Why is what happened yesterday fixed, while what will happen tomorrow is uncertain? The answer to this question is often entropy. As disorder increases, systems become more complex, which is why time appears to be unidirectional. However, this explanation applies to large systems, to omelets, engines, stars, not to a single quantum particle. When you completely isolate a photon, entropy is no longer a guiding principle. The line between before and after blurs. And it is precisely in this blurred region that experiments whisper to us future choices may be related to past behavior in ways far stranger than we imagine. To understand this, we need to go back to physics' most infamous crime scene, the double-slit experiment. But this time, we will examine it not like a textbook diagram, but like a detective trying to figure out where things went wrong. Because if we find what went wrong, we can understand why it went wrong. And that's where the story really begins. In the next chapter, we will see step by step that the double-slit experiment is not just a question of wave or particle, but actually a trap that questions time itself. Imagine a wall. Now imagine you are firing projectiles at this wall from behind a barrier riddled with slits. Some bullets will hit the cracks and stop. Some will pass through. And in the end, you expect to see two distinct strips of bullet holes side by side on the back wall, just as common sense and classical physics would predict. This is simple, solid, predictable. That's exactly how matter behaves in the everyday world, and we live assuming that these are the rules of the universe. But everything changes the moment you start shrinking the bullets. When you reduce the size to the scale of an electron or a photon, the rules you know now quietly disappear. Instead of two strips, when you look at the wall, you see a complex, wavy pattern of interlocking, swirling waves, like the ripples created by two stones thrown into a still pond colliding. This image tells us something very clear. The particle did not pass through just one slit. It did not pass through either one slit or the other. It passed through both. It behaved like a wave, splitting itself interacting with its own possibilities, and finally hitting the wall not as a solid object, but as a spread out cloud of possibilities. But here's where the real critical point begins. If you place a detector, a sensor, or a simple camera next to the slits, and try to observe which slit the particle passes through, this wave behavior instantly ends. The particle, as if it has changed its mind, suddenly stops being a wave and transforms into a solid, singular projectile. Now it only passes through one slit, and that complex interference pattern on the back wall disappears. It is replaced by two boring but familiar stripes. Stop for a moment to think about what this means. It means the particle decides how to behave depending on whether it is being observed or not. When you're not looking, it's like a ghost, trying all possible paths at once, exploring every possibility. The moment you look, it locks onto a single reality and freezes. Measuring it forces it to choose what it does. That's already strange enough in itself, because this implies that the particle's history, that is, the path it followed, is not fixed until you ask the question. But physicists are stubborn people, so they didn't stop there and asked a more unsettling question, a question that began to open the door to the concept of time. What if we wait? In 1978, the legendary physicist John Archibald Wheeler, who worked with Einstein, found a way to push this strangeness to its limits. He called this idea the delayed choice experiment. The logic was simple, but the consequences were devastating. In the standard double-slit experiment, we decide whether or not to observe the particle before it passes through the slits. We set up the detector, then we start the experiment. The particle sees the detector and behaves like a bullet. If we remove the detector, it behaves like a wave. But Wheeler asked, what if we trick the particle? What if we let it pass through the slits first? Imagine the particle has already crossed the barrier. At that moment, it should have already decided whether it would be a wave passing through both slits or a single particle passing through only one slit. It would now be on its way, heading towards the back wall. And that's exactly when we decide whether to observe or not. So we make a choice in the present about an event that happened in the past. If the universe respects the unidirectional flow of time, this shouldn't matter. If the particle passed through both slits as a wave, a detector that is switched on later cannot change that. It's too late. The trace has already been left. But Wheeler predicted that the universe didn't work that way. If you choose to measure a particle's path after it passes through the slits, the particle, as if going back in time, alters its past behavior to match your choice today. It decides retrospectively that it was a single particle. Wheeler envisioned this idea on a cosmic scale. Consider a single photon emitted from a quasar a billion light years away. That photon needs to travel around a massive galaxy to reach Earth, and gravity gives it two different paths, left or right. It travels for billions of years, and today it reaches our telescope. At that very moment, we decide whether or not to measure which side of the galaxy it came from. According to Wheeler, our choice today determines whether that photon behaved as a focused particle or a radiating wave for billions of years. Feel the weight of that. This means that the history of the universe is not a completed record, but rather a live broadcast, moment by moment, governed by our choices. For a long time, this was just an uncomfortable thought experiment on paper, until technology caught up. To test this idea in the lab, a way was needed to delay the observation decision without touching the particle. That's where the quantum eraser comes in. Although its name sounds like a science fiction weapon, it's actually an incredibly clever engineering marvel designed to cheat causality. You pass a laser through a double slit, but behind the slits, you place a special crystal, a beta barium borate crystal. This crystal does something extraordinary. It splits each photon in two. The result is two entangled photons that cannot be separated. These are lower energy photons, but their fates are locked together. They are like twins. One is called the signal photon, and the other the stray photon. And here's the key point. The signal photon is sent directly to the detection point, that is, the back wall. The universe isn't as lonely as it seems. Quantum entanglement shows that even distant particles are interconnected. Distance and time are just an illusion. This discovery opens a door for anyone who wants to understand the mysterious order of nature. If you too are curious about these fascinating secrets of the universe and want to feel the real connections, subscribe to our channel and share the video so that others can also benefit from this unique information, because some secrets multiply when shared. The screen is no longer just a surface. It's a silent witness recording what's happening. The signal photon falls there, leaves a trace, and in our language, dies. Like an event in history, it leaves behind a moment that we assume is irreversible, indelible, and unchangeable. We look at that spot, say, yes, it hit here, and our minds register this information as certainty. But the experiment doesn't end there, because the remaining photon is the true carrier of the story. It's an informant silently carrying information about which slit the signal photon passed through. And if we know its path, we also know the signal's path due to entanglement. These two are no longer separate entities. The connection between them is limited by distance and time. That's why we don't immediately capture the remaining photon. We deliberately delay it. We extend its path by routing it through fiber optic cables, mirrors, and complex optical labyrinths. This saves us time. More precisely, we're leaving a void in the universe. Meanwhile, the signal photon has already hit the wall. The event is being recorded. There's a point on the screen, a coordinate, a fact. On a human scale, this happened very recently, but on a quantum scale, almost infinity. That point is now like ink, fixed, frozen, motionless. The past is locked, and right now, the idle photon is still traveling through fiber optic cables. Technically, it's in the future compared to its twin. It hasn't reached any detector yet. No decision has been made yet. The universe is holding its breath right now, because we're doing something here that disturbs the human mind. After the signal photon hits the ground, we now have a choice. Either we send the motionless photon to a detector that preserves the path information, or to a scrambler that irreversibly destroys this information. Imagine you freeze time for a moment. The signal photon is on the screen, at the X coordinate. This appears unchanging. According to classical logic, what we do now shouldn't matter. A trace remains. When the trace is erased, the trace will not change. But this is where the quantum eraser comes in. The question the experiment asks is extremely simple and equally dangerous. Can the signal photon know what will happen to its twin in the future? If the answer is yes, then what we call cause and effect doesn't work as we think. If the answer is yes, the future can touch the past. and this shakes almost all the assumptions upon which the human mind is built. The free photon travels rapidly through fiber optic cables, reaching a point where transparent mirrors and beam splitters converge. These are our selection mechanisms. If the photon is directed to specific detectors, let's call them D3 and D4, the path information is preserved. The universe holds the answer to the question, which direction? In this scenario, we would expect the signal photon to behave like a particle in the past. And indeed, when we look at this group, there is no interference. There is only clustering. Solid, clear particle behavior. But there is another possibility. The beam splitters can be adjusted to completely mix the information from the left and right slits. Such a mix that it becomes physically impossible to tell where the photon came from. The information is erased, irreversibly. This decision is made randomly. No one forces it. In more advanced experiments, random number generators are used to make the decision in the last nanosecond. Thus, even human will is eliminated. And here's the critical moment. This erasure occurs after the signal photon hits the ground. The signal photon is now history. But when the data begins to be collected, something incredible emerges. Viewed in isolation, the signal image is just a chaotic mass of light. There is no meaningful pattern. But when the data is separated, the signals in the group where the path information was preserved behaved like particles from the past. The signals in the group where the path information was erased behaved like waves from the past. It's as if the signal photon looked at the fate of its future twin and decided how to behave in the past accordingly. This is not a metaphor. This is a result that has been repeatedly confirmed with graphs and statistics. The choice made in the future determined the reality of the past. And that's why not everyone says it out loud. Because this experiment questions not only physics, but also time, causality, and humanity's role in the universe. And not everyone can answer all the questions at once. This is where intuition comes in. And intuition whispers, what's happening here contradicts everything classical physics has taught us. Because in our world, causality is unidirectional. You push something, it moves. Pushing is the cause. Movement is the effect. Just like dominoes, one falls, then the next. The cause always comes first. The effect follows. What we call time is precisely this sequence itself. But the quantum eraser disrupts this order. It does something even worse. It mocks this order. Here, the effect, the pattern on the wall, physically occurs before the cause. The result is recorded even before the decision to erase the information is made. Like writing yourself a letter yesterday and mailing it today. The timeline curves in the opposite direction. This leads us to the thought. Perhaps time isn't a straight road where dominoes fall one after another. Perhaps time is a network under tension, its head vibrating when you pull on its edge. You touch a point, and the effect propagates both forward and backward. So the question is, how can a photon do this? Is it intelligent? Does it understand the information? Does it see the future? No. There's no consciousness, no plan, no will. There's only a subatomic particle. And yet, the correlation is perfect. When the path information is erased, whether a second later, a year later, or across an intergalactic distance, the matching photon seems to behave like a wave from the past. When the information is preserved, the matching photon behaves like a particle from the past. Time doesn't matter. Distance doesn't matter. The universe seems to maintain a hidden consistency. It's as if it's saying, if you have the power to know, I won't show you the wave. If you can understand the path, I will close the possibility. The key word here isn't when. What matters is that it's knowable. As long as information exists anywhere in space-time, in the past, present, or future, probability collapses. Reality reacts to the existence of information. But we must stop here, because at this point, you feel the mind immediately veering in a dangerous direction. So we can build a time machine, so we can change the past, so we can predict the outcome. No, there's a crucial limit here. When you look at the signal screen, the raw data, you see nothing. Neither wave nor particle, just a gray blur. Because the two patterns, wave and particle, have superimposed and canceled each other out. The true pattern only emerges when it's retrospectively extracted from data from future detectors. That's why you can't send messages to the past using this mechanism. You can't look at a screen and say, I see a wave, so the information will be erased tomorrow. You don't see a wave, you only see noise. Without the key to the future, the message from the past cannot be deciphered. Physicists call this the no-signal theorem. This principle saves relativity. It prevents grandfather paradoxes. It prevents the universe from completely spiraling out of control. But, and this is very important, it doesn't eliminate strangeness. It only makes it practically unusable. Just because you can't send messages from your phone doesn't mean there's no connection. The connection is still there. The future event and the past event are mathematically locked together. The universe still connects the two ends of time. It's just hiding the evidence, like a perfectly executed crime. The event happened. The timeline is broken. But the evidence is encrypted with a key that doesn't yet exist. The key will only appear in the future. Now we need to stop and ask, what does all this mean for our lives? We are used to thinking of the past as a finished painting. The paint has dried, the colors have settled, the artist has put down the brush. We can neither move trees nor change clouds. We say that the past is a solid record of things that have happened and are over. But the quantum eraser whispers something quite different. The past is not a painting. Perhaps a Polaroid photograph. The image is there, but blurry. It is there, but not yet clear. It hasn't yet decided exactly what it wants to be. And this blurriness is preserved until something in the future interacts with it. This means the consequences of an event that happened yesterday may not yet be complete. It may hang in the air like a ghost. A choice to be made tomorrow may finally clarify its meaning. And this thought shakes the idea of linear time. Because if this is true, the past isn't as over as we think, and the future isn't as far away as we think. Perhaps we are standing right in the middle of a time knot. The timeline. In the world we've been taught, everything moves in a straight line. A cause is B. B gives birth to C. First comes the cause, then the effect. This chain is unbreakable. Our logic, our memory, and our sense of identity are based on this order. But here, in the world whispered by these experiments, the direction of the chain blurs. Here, C seems to be leaning into A's ear and whispering something. The end of the story affects how the beginning is written. The ending adds a note to the beginning. This is what physicists call reverse causality. This isn't time travel like in Hollywood movies. You don't jump into a machine and go back in time. You don't kill anyone. You don't create paradoxes. This is a much quieter, much deeper, and much more disturbing experience. The timeline here behaves not like a rigid road, but like a taut rope. When you pull one end of the rope, it's impossible for the other end not to vibrate. It doesn't matter which end is the past and which is the future, because the rope is one. The vibration spreads in both directions. The moment a free photon chooses its path in the future, it pulls this rope. And the signal photon that hit the wall and died in the past feels this pull. Its behavior seems to be shaped to match this choice that hasn't yet happened, as if the past has already accepted the pressure of the future. From this perspective, history is not a chain of falling dominoes. Reality is a handshake, but not an ordinary handshake. A handshake that passes through time. The past extends its hand. The future responds. And only when these two hands come together does reality become certain. Until that moment, everything is a possibility. Everything is smoke. Everything is an unfinished sentence. You might think your past is etched in stone, but physics might be telling you that you haven't finished the story yet. Perhaps your past is waiting for you to decide what you will do in the future. At this point, you might want to hope that this is an overinterpretation. You might want to say, this must just be speculation. You might want to think, serious scientists wouldn't accept this. But the truth is, the opposite is true. There are serious mathematical models that have been developed over decades to understand this idea. One of the most striking of these is the two-state vector formalism, developed by Yakir Aharonov. And this name cannot be underestimated in the field of quantum fundamentals. In standard physics, we describe a system with a single-state vector. It starts from the past and moves towards the future, just like an arrow shot from a bow. To know where the arrow is, we calculate where it was the moment it hit the target. This is how we send rockets to the moon, drive cars, and build bridges. But Aharonov said, this picture is incomplete. A quantum system cannot be described by a single arrow. Two arrows are needed. The first is the arrow we know. It comes from the past and moves toward the future. But there is a second arrow, and this arrow starts in the future and moves toward the past. Think about this for a moment. The moment you are in right now is not just the result of your past. It is also influenced by your future. What you have experienced since you were born defines you. But things you haven't experienced yet also define you. The present moment is the point where these two arrows collide. It is a collision field, the only point where the past and the future touch each other. This perspective perfectly explains the quantum eraser paradox. Why does the signal photon know what the idle photon will do? Because information propagates backward from future measurements. The selection made in the detector creates an effect wave that travels backward in time. This wave reaches the signal photon in the past and informs it how to behave. There is no magic here, no consciousness, no hidden entities, just a symmetrical universe where time flows in both directions, just like traffic flowing on a two-way street. We only see our own lane. We don't notice oncoming vehicles, because our brain is programmed to read the book from beginning to end. But the universe reads the whole book at once. Of course, skepticism kicks in. The old experiments were flawed, it is said. The equipment was inadequate. The lasers weren't properly aligned. These objections are valuable. Skepticism is what sustains science. But in this case, skepticism has hit a wall. The delayed selection experiment not only survived the criticism, but returned even stronger. In 2007, a team led by Vincent Jacques conducted a highly rigorous version. They verified single photon sources with extraordinary precision. They left no room for doubt, and the result remained unchanged. Future selection determined past behavior. In 2013, Xiao Song Ma and his team took the experiment a step further. They separated entangled photons by kilometers. They sent them to different laboratories. It was physically impossible for a classical signal to pass between them. They achieved nanosecond synchronization with atomic clocks. They ensured that the selection was made immediately after the event. But the universe didn't back down. The interference pattern only appeared when future measurements allowed it. Particle behavior only appeared when future measurements required it. The data was flawless. It wasn't a statistical error. It wasn't a software error. This was a fundamental characteristic of the reality we live in. The question is no longer, is this true? That stage has long passed. The real question is, what do we do with this? The real question we should be asking is this: why are we so afraid to accept this? And why does our mind cling so tightly to this idea, as if our identity would vanish the moment we let go? When evidence whispers that the linear perception of time might be an illusion. Perhaps it's because the alternative is not only different from what we're used to, but also far heavier than our minds can bear. For if the future is real enough to influence the present, if events yet to happen can send waves into the present, then we must confront an inevitable question. Perhaps the future is already written. And this thought leads us to the most unsettling, coldest, and most terrifying concept in physics for humanity: the block universe. If time is symmetrical, if the future exists as firmly as the present, then the idea that time flows collapses. No river, no flow, no movement, just a frozen structure. To understand this, set aside abstract concepts for a moment and imagine something very simple. Imagine a long rectangular loaf of bread. Suppose you slice this bread into thin slices. Each slice represents a single moment in time. One slice contains the age of the dinosaurs. One slice, the Roman Empire. One slice, the thoughts that crossed your mind as you ate your breakfast this morning. And another slice, your funeral 50 years from now. From your perspective, you feel like you're passing through the bread, as if there's only one slice and the next slice doesn't exist until you reach it, as if time is moving forward with you. But the block universe says, the bread is already there. The beginning is there. The middle is there. The end is there. They all exist simultaneously and are all equally real. We are frozen within the four-dimensional crystalline structure we call space-time. The dinosaurs are still alive in their time period. In your future time period, you are already dead. And in fact, nothing is moving. Nothing is changing. The only thing moving is your consciousness. Your awareness moves like a beam of light falling on a film strip on this massive block. The film has already been shot. The script has been written. The final scene has been determined. You just think you're watching the film for the first time. Quantum erasure experiments are in surprising harmony with this eerie picture. Because the fact that a measurement made in the future can affect an event in the past means that the future is sufficiently solid, sufficiently real. The events of tomorrow seem to be there, waiting for us to reach them. And if this is true, a question arises that we can no longer escape. What will happen to free will? If information from the future is shaping the present, were the choices you thought you were making really choices? Or were you simply following a path that already existed within the frozen block structure? Were you a line of code written before the universe even began? This is the price of understanding quantum mechanics. You see the inner workings of mechanics, but you lose the warmth of your own will. You realize you could be a character in a printed book, and no matter how hard you try, you can't change the words already written on the page. But the story doesn't end there. We've fragmented time. We've turned it into a prison. And if you think that's claustrophobic, you're about to face a far more disturbing reality. Because now we're beginning to tear down the walls of space. At least in a prison, you know where the walls are. But in the next paradox, we'll discover that the walls don't actually exist at all. We escape the prison of time and step into the vast emptiness of space. If time is a river propelling us forward, then space is a wall separating us. Or at least, that's what we assume. I am here. You are there, in front of the screen. The wall is behind you. There's distance between us. And that distance provides a sense of security. In the classical world, distance acts as the ultimate buffer. If you want to affect something, you have to touch it. If you can't touch it, you have to throw a stone. If you can't throw a stone, you have to send a signal, a sound wave, a radio wave, a beam of light. And they all have one thing in common. They all take time to travel. Nothing happens instantly. This is considered one of the fundamental laws of the universe. It even has a name: locality. This was one of the cornerstones of Einstein's theory of the universe. The idea that nothing can travel faster than the speed of light. If the sun were to explode right now, we wouldn't know it for 8 minutes. During that time, we would continue to see its light, feel its gravity, and live in blissful ignorance, because information has to travel through space. But quantum is about to turn this story upside down. A pair in Tokyo stands out as a completely unique entity with its distinctive texture, taste, and color, while another pair in Rio de Janeiro is notable for its unique character, slightly acidic taste, and unparalleled texture. However, these two pairs communicate with each other in no way. Unaware of each other's existence, they whisper to one another, existing in complete isolation, like hundreds of small, independent islands in the dark ocean of space. This idea of separation reminds us of humanity's small and insignificant position in the universe, sometimes deepening the feeling of loneliness. Yet, our daily experiences logically confirm this. In classical physics, objects are independent of each other, so you don't expect your glass to spill just because someone else's glass spills on another continent. The effect of one event can only reach another through physical contact or exchange of information. But quantum mechanics shatters the boundaries of logic and habit. It overturns our ordinary perception, takes us beyond the limits of logic and experience, and reveals an entirely different universe before our eyes. In the 1930s, physicists discovered a phenomenon that seemed mathematically impossible, but was experimentally confirmed. Under certain conditions, two particles can interact with each other, then separate, but never become completely independent. They are connected by a bond beyond classical communication pathways, as if there were an invisible string between them, and are no longer two independent objects, but different parts of a single whole. Consider an example to illustrate this. You take 2 dice and shake them on the same table. Then take one to Sydney and the other to Cape Town. They are thousands of kilometers apart and completely isolated. When you shake the die in Sydney face down, and at the same time, without a single nanosecond delay, the die in Cape Town gives the same result with perfect inverse correlation. As if there were an invisible telepathy, distance becomes an illusion. Space itself loses its meaning for these particles. The laws of classical physics become invalid here, and Einstein called this phenomenon the spooky action at a distance, because this connection seemed to exceed the speed of light limit and shake the safe and logical structure of the universe. Einstein developed a defense to protect his mind. This isn't magic, it's just a lack of information, he said, and put forward the hidden variables hypothesis. Much like putting 2 gloves in 2 separate boxes, mixing them, taking one to Mars and the other to Venus, and not knowing which glove is where until you open the boxes. Particles move according to a predetermined scenario from the moment they are born, and we cannot see this scenario. Everything is predetermined. Locality is preserved. The universe is safe, and there is no terrifying instantaneous connection. There is only invisible information, and physics works in a logical and comforting way. However, in the 1960s, a physicist named John Stuart Bell asked a question that would overturn Einstein's safe world. Is there a difference between the hidden variables scenario and true quantum entanglement? Can we demonstrate this experimentally? This question shook Einstein's comforting explanation because Bell proved that it was mathematically possible and proposed the magic square game to demonstrate this difference. Imagine 2 players, Alice and Bob, in separate rooms without speaking or communicating with each other, each given a 3x3 square and asked to draw plus and minus signs. But quantum mechanics accomplishes this in a way that is impossible to understand with classical logic, yet perfectly consistent with quantum mechanics. In the world of hidden variables, they could have planned this beforehand, but in the quantum world, the particles seem to play their own game. And the results reveal a frightening but undeniably observable truth that always transcends classical logic. Even if they develop strategies, even if they make plans, classical logic limits them, because mathematically it is impossible to create a perfect table that satisfies every rule simultaneously. Music. This applies to all rows and columns. No matter how hard they try, no combination of numbers can satisfy all the rules at once. This shows the maximum success rate they can achieve with a classical strategy, approximately 89%. Failure at some point is always inevitable. Mathematics forbids perfection. But when Alice and Bob are given entangled quantum particles, things change completely. The particles begin to achieve something that logic and classical probabilities do not allow. The possibility of losing disappears. Now, to understand why this is so, let's look at the structure of the game. We have a grid of 9 squares, and we need to place either +1 or -1 in each square. The rules say that the product of each row must be +1, and the product of each column must be -1. Try this on a simple piece of paper. You can fill the first few rows and columns. But when you get to the bottom right corner, you encounter a contradiction. You need to put +1 to satisfy the row rule. You need to put -1 to satisfy the column rule. Both signs don't fit in the same box. It's mathematically unsolvable. Music. So there's no pre-prepared table. A perfect solution that Alice and Bob can memorize is impossible. If they try to agree on a strategy before going to their separate rooms, they will inevitably fail at some point. The predetermined numbers don't match the referee's demands. In the classical world, the maximum success rate is 89%. That's the absolute limit allowed by the hidden variables. If Einstein were right, the particles should be placed in boxes like gloves, and each should act according to a predetermined scenario. Alice and Bob would have to lose 1 out of every 9 games. Logic demanded it. But quantum mechanics challenges our logic. Now let's give Alice and Bob a quantum advantage. Entangled particles. They take 2 pairs of particles into separate rooms. There's no strategy, no plan. They're not entirely sure which numbers to write. Their minds are blank. Their papers are clean. The referee asks Alice to fill in a line, but Alice doesn't look at her cheat sheet. She measures her particles, and the measurement gives a random result depending on which line she fills. She writes either +1 or -1. Just then, the referee asks Bob to check the column multiplication. Bob measures his particles, and the result is also random. But the magic begins here. The particles are entangled, meaning the results are not independent, but rather interconnected. Alice's measurement instantly gives Bob a consistent result. Walls, oceans, distances don't matter. The particles express themselves. Mathematics shows that when this quantum strategy is used, the results will always conform to the rules. The line multiplication is +1, the column multiplication is -1, and the intersection points always match perfectly. They win 100% of the game. An outside observer might see this as cheating, as if they'd buried a wire under the table. But there's no wire. There's a truly unsettling connection between quantum entanglement and what physicists call quantum pseudo-telepathy, a fitting name. It's not true telepathy, because Alice can't send messages to Bob using particles. Measurements control randomness, and communication is blocked. But they act as if they were a single mind. Their actions are coordinated harmoniously without information sharing. Even though Alice and Bob are in separate rooms, unable to speak, completely isolated from each other, the particles speak. Information doesn't travel from Alice to Bob because they aren't different parts of the universe, but 2 ends of the same whole. Entanglement eliminates distance. By its very nature, distance is 0. This refutes the idea of locality. In classical physics, objects only affect their immediate surroundings. But quantum pseudo-telepathy shows that the universe is fundamentally not local, that everything is interconnected as a single holistic network. When you make a measurement at one point, all parts of the network are affected. To test the strength of this connection, scientists launched a satellite in China in 2017 called MSUS. It was designed to send entangled photons to Earth. One station was in the Himalayas, and the other was more than 1,000 kilometers away. Despite being separated by the vacuum of space and the Earth's atmosphere, the particles remained connected. Quantum entanglement completely overcame the limitations of classical logic, making instantaneous coordination possible even across continents. Scientists use the universe as a giant random number generator to test the limits of quantum entanglement. They pointed their telescopes at quasar planets billions of light years away and used the color of light from these ancient galaxies as a random trigger to determine how particles were measured. This method, called the cosmic bell test, guaranteed that the measurement decisions of entangled particles on Earth were determined by light from a distant quasar billions of years ago. If entanglement were a sham scenario, a conspiracy must have been hatched long before Earth was born. But the result was astonishing. The connection still persisted. The universe was forcing particles to behave as a single unit, even if the instruction came from the edge of the visible universe. This experiment showed that quantum entanglement was not just a lab error or coincidence. The violation of locality was a fundamental property of the universe. It encompassed galaxies, ignored time and distance, and bound the universe together in a way Einstein never wanted to accept. Although space appears to us as a vast emptiness, for quantum particles, distance is negligible. The question that arises here is a paradox that both fascinates and amazes the human mind. If particles can communicate instantaneously between galaxies, why can't we use this to send messages? Why can't we build a quantum phone that exceeds the speed of light? The answer is simple. The universe forbids it. Quantum connectivity exists, but because it is entirely random, it is uncontrollable and cannot violate causality. You cannot send messages. You can only observe correlations. This is one of physics' most delicate balancing acts, a kind of peaceful coexistence between quantum mechanics and special relativity. While quantum mechanics speaks of instantaneous connections and the insignificance of space, special relativity reminds us that no information can travel faster than light, and that cause must always precede effect. The fact that Alice and Bob are in separate rooms, taking measurements at different times, does not change the connection between the particles. Although the change is instantaneous and real, the result is entirely random for each particle. The universe, while enabling connection on one hand, simultaneously prevents communication on the other. It maintains the speed of light by hiding behind a wall of randomness. Essentially, the universe says, you can connect, but you can't send messages. To visualize this idea, the famous physicist David Bohm used an aquarium analogy. Imagine a fish tank with a single fish swimming in it. You are watching it on two separate monitors placed on the front and side of the tank. On the front camera, you see fish A. On the side camera, fish B. Because you are looking from different angles, they appear as two separate fish. But if you watch carefully, you notice a surprising relationship. Fish A turns, fish B turns at the same time. A jumps, B reacts instantly. If you didn't know the actual structure of the tank, you might think the two fish were communicating through an invisible telepathy. Quantum entanglement teaches us the logic of the universe. Things that appear separate are fundamentally interconnected. Distance and time are limitations of our perception. The universe coordinates all its parts as a single whole, but it doesn't do so in a way we can control. Quantum mechanics reveals to us a mysterious yet perfect order in nature. Everything seems random, but is actually interconnected by an invisible harmony. And perhaps the most fascinating fact is that our connection to the farthest corners of the universe continues to exist beyond our perception, beyond time and space.